But anyway, okay, so let's talk about error correcting codes a little faster than I had anticipated. Okay, so good, good, good. Okay, so let's talk about this. Okay, so this is actually kind of like a very practical, basic problem. Uh, so it's a problem of imperfect communication. So you have one person in location A and one person in location B, and they say something over a telephone wire, but the telephone wire has been bitten by rats or something, so some bits get flipped. Yeah. I mean, I always think of like I remember elementary school, like they always claim that you could take like two plastic cups and attach a string and like you can connect it to your friend's house next door and it works as a phone. Do you guys remember this? Yeah, but like I didn't have any friends next door. So like never really tested it. So I never really believed this. But you can imagine, this is some kind of flimsy string with two plastic cups. In our model, you're gonna set some m-bit message or whatever you send, every bit will get flipped independently with probability p. Okay, this is a good initial model. And then people study things like, oh, out of m bits, a p fraction is adversarially chosen and things like this, more complex models you can imagine. But today we're just doing every bit gets flipped with probability p. Yeah. All right, so, okay, so, all right, so if you are, talking to your friend and the connection's really bad because you're in between Purdue and Indianapolis and there's like this dead zone, and you're not going through, you're not getting your message through, what do you do? What could you do? Hang it well, okay, without hanging up, trying in. Repetition, you probably repeat the same thing over and over again, or like you're talking to your elderly relatives and you're like, and you're like, why? You're like, and you just like keep repeating until they like kind of give up. Okay, so repetition is like one way to get over flimsy community. If I say the same thing 5 times, I'm hoping you'll take the average of what I say and it'll register, right? That's called teaching. And okay, so in the more general thing, right? You have some message you want to send, but you might encode it. The simplest encoding is you might just repeat the message 5 times, and the person on the other end can just take the most common bits or something. Okay. So, but in a general scheme, person A has a message. We encode it into probably a bigger message to add some kind of redundancy, and you're hoping that even as some bits flip, you can recover the original code. Okay. So like if you're promised that only one bit flips or a very small number of bits flip, if you just repeat the message 3 times and take the majority bit, you're going to be okay and things like this. Okay. So what we are interested in though is, we want to do something more clever and just repeating the message over and over again. Okay. So we want kind of to think about that ratio of what you're trying to send to how many bits you need to send it to have some kind of success probability. So, yeah, so formally, how do we model this? We have an encoder. It takes your m-bit string and writes it as an n-bit string. You have your decoder, which goes in the opposite direction, n-bit string down to m. So n is going to be the bigger one. Okay. And then we'll have to model the bit flipping, I'll have a noise function. So this is like a random function, kind of different than like what we said when we was a hash. It just takes a bit string and it'll randomly flip every bit with probability p. Okay, so it's not really like a function in the natural mathematical sense, but I think you'll see what I mean. So what does this represent? I take x, right? And I encode it. And then as it goes over the cable, some noise flips some bits. And then I can't, my hands aren't big enough. And then I decode it. Okay. X, encode, noise, decode. You're hoping to get back the original message X. Okay. All right, good. Okay, so I guess I drew a picture. Did I draw a picture? Yeah, so it's something like this. X, in your smaller space is going to get mapped to some code word in the bigger space. Okay? And some point here in the message space is going to get, or code space is going to get decoded into the input space. And then one thing to point out is like, well, this is smaller than this, so this is going to be 1-to-1, but this will be many to one. Okay, so other points will also get mapped uh, into y, or maybe you do like a geometric thing where you're going to say something like, oh, what's behind here? Okay, you're going to say like this whole circle maps to y. Yeah, this whole region is going to map to y or something. Okay, so that's sort of what the encoder and decoder would visually look like. And so what we're interested in is, so you're trying to send 10 bits, but you need 20 bits to send it over to wire or something. So the transmission rate is 1/2. Okay, so it's always some value between 0 and 1, and higher is better. Okay, because throughput will be like the reciprocal or something. Okay, so you want higher transmission rate, but then it needs to, up to some guarantee, you succeed with some probability. Okay, and good. So now the average error rate, we're going to do something that's a little bit different in the sense that we're not going to do worst case in the usual sense we kind of do, although your homework will address this to some extent. So in this model, we're going to take kind of the error rate, but on average over all inputs. So you can think of it as I choose a random input message, and the randomness is over the noise. So if I choose a random input message, code it, apply random noise, and decode it, do I get back the original randomly chosen thing? Okay, so you can think of x as being randomly chosen, or you could think of us as taking the average error over all x that's the same. Okay, good. On homework, you are going to figure out how to uh, take what we did and enhance it a little bit so that you can get for all x, the error is something, something. Okay. It's more closely related than you might expect, but I'll leave that for you to figure out. Okay, so that's the basic problem, and this was a practical problem. Is one point I want to make. In the 20s, 30s, 40s, when they're building out the first phone networks across the country, or Telegram, or whatever beep 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 stuff like Morse code stuff, Telegram, I guess. Okay, so this was a very practical problem, and at some level, it was just okay, let's just lay more wire, let's try to get like higher quality metal or something. Um, it was an engineering thing, and people would just try stuff and make some incremental improvement. But I think for a while there, it wasn't really studied that formally. It seemed practical. Some improvement here seemed to be worth a lot of money given how important telephones were becoming, um, or whatever communication was becoming. But at some level, it wasn't a real mathematical subject in many ways, right? And so I want to set that as a scene because I think what we're doing today is more than just some result, but it's also somebody taking something very much of common interest and then turning into a field. Okay, so that happened in this famous paper by Claude Shannon, dated, should be in the 30s. Oh, 1948. Okay. All right. So Shannon took this model, and I think he also made clear the model. Maybe the model wasn't even clarified before this. In general, they're just trying to send messages over wires. Okay. And he wrote this very important paper. Uh, but he gave a theorem. He took something that, a bunch of wires are being connected together and people don't know why messages are getting garbled, and he outputted a theorem. So even without telling you what the bound yet, uh, for starters, he already has the words optimal transmission. So transmission, he has some kind of defined quantity that we just went over, and he has the word optimal. So he's going to get type bounds for something that people didn't even know was a real thing. And the bound he got, okay, it's a little bit mysterious at this point, is 1 minus what's called the entropy for P. Okay, so for the moment, it's just an equation, which is P log 1 over P plus 1 minus P log of 1 over 1 minus P. Okay, so somehow he got this kind of magic optimal transmission, whatever this quantity is. He showed you can't do much better, and you can't do better, and you can do that well. Okay, so we're going to do both an upper and lower bound, and at some level that there is some kind of golden, this looks like a law, right? This looks like something fundamental to this very basic model of communication. I don't know if people were expecting like a law to emerge, right? This is some hard limit for this particular model. Okay. Okay. I should note that this paper is very cool. I don't know if it's well, okay. I think let me at least point out something on this first page. Uh, the choice of a logarithm base 2 corresponds to the choice of a unit for measuring information. Base 2 is used resulting means called binary digits, or more briefly, bits, a word suggested by Tukey. So the word bit was relatively new. Tukey is also at Bell Labs, did fast Fourier transform and some bunch of other things. Okay. So this is really at the beginning of thinking about quantifying, taking seriously, modeling in some way information. Okay. Also in this paper, he makes language models towards the back of the paper. So he actually made a 1-gram model, 2-gram model, 3-gram model. We actually took an encyclopedia and just statistically tried to figure out, okay, what's the most likely letter after A? Most likely, he did all the probability tables. And he actually built a 2-gram, 3-gram, 4-gram model by hand. And you could see the sentences starting to get a little bit better. But he made a statistical language model, one that was operating just on statistics, right? Which kind of disappeared for 50 years of old-fashioned AI and is now obviously back in full range, right? So we kind of are living in Shannon's world right now, just with GPUs. Okay, good. So it's a great paper. Okay, so he proved two bounds that we're going to do in class. We might do 15 minutes less than I expected, but we're going to do two bounds in class, an upper and lower bound. Upper bound is maybe the more fun part. So for all delta greater than or equal to 0, there is a coding scheme with transmission rate at least 1 minus HP minus delta, and average error less than or equal to delta. Okay, so you can get arbitrarily small error and arbitrarily close to 1 minus HP in the transmission rate. Now, one thing I should point out is in this model, you're allowed to make M and N bigger, and we will do that. So for a sufficiently large M, you can get this transmission rate. Okay. All right, so you can get coding schemes approaching 1 minus entropy in transmission rate and error going down to 0. And then he also showed that any coding scheme with transmission rate, at least this thing has average error greater than delta. Okay, yeah. No. So we're really saying that 1 minus HFP is tight. So you can't do much better than 1 minus HFP, and you can get arbitrarily close to 1 minus HFP. And I think actually here, average error, we're going to actually get this to be arbitrarily big. But anyway. Okay. Good. So those are just the two halves that kind of generate this word quote unquote optimal. All right, so let me explain a little bit. Let me just define what entropy is and a couple nice properties about it. And then if we have time, we'll do some of that analytical stuff with entropy towards the end. Otherwise, follow up and read the section in the notes. Okay, so it's some measure of the randomness in a random variable, or some attempt to quantify the randomness in a random variable. There's probably many possible ways to do it, but for some reason this way has really stuck. So let X be a discrete random variable. I'm going to find something else first. It's sort of a made up word, but I find it helpful. So I'm going to define like a shock variable. So when that you have some random variable and some outcome occurs, right? And if it's something that like happens all the time, you won't be that shocked. But if it's a very rare event, you'll be more shocked. Okay, so in that sense, I wrote f of x is that random variable where based on the outcome, you do 1 over the probability of the outcome that happened. Right? So x takes on some value, but then you look back and you say, what was the probability of that happening? And shock will be 1 over this, right? Okay, that's just a made up word. It doesn't exist anywhere on the internet, but I find it helpful. And Now the entropy is going to be defined as the expected value of the logarithm of this quote unquote shock. Okay, so if I expanded that out, that'll look something like the expected value of the log of 1 over probability that x is equal to x. A little bit confusing. So x is a random variable. It takes on some value. Then afterwards, you look and see what was the probability of that happening. And okay. All right. So good. Um, okay, so that's probably kind of mysterious. Let me give an example. Uh, so for a coin that flips heads with probability p, and you expand out this expectation. So with probability p, you get heads. Your shock is 1 over p, and log of 1 over p. With probability 1 minus p, you get tails. The shock is 1 over 1 minus p, and you take the log. Okay, so that's how entropy is defined. In this case where the x is just a Bernoulli variable with probability p comes up often, and people often just write h of p instead of h of x, where x is a random variable that flips heads with probability p. Okay, so a little mysterious. Here are some. Okay, now on top of entropy, one can define conditional entropy. Okay, so you just treat a conditional random variable as a random variable, and uh, yeah, okay. So now this is a little bit confusing because if you look inside here, this will be kind of the expected value over x times the expected value of y, the log of, and then if I expand out the shock, it'll be kind of like the probability that y takes on that value that occurred given x. Okay, it's sort of this crazy thing. Okay, now let me point out a couple properties, and then we'll come back to prove it if we have time. So one thing is you can work this out kind of nicely. So you can have the entropy of two random variables where you just treat them as a joint random variable. And if you work through the definition slowly, you'll find that the entropy of x and y together is the entropy of x plus the entropy of y given x. Okay? If I just replace the word entropy with information, this almost makes sense. The total amount of information you can get out of x and y is first the information you got from x, or you can get from x, plus the information you can get out of y, but you've already seen x. So it's y conditional on x. Okay, again, we're using information kind of vaguely. It's not clear what information means, but it seems mildly intuitive, right? We're taking something quite abstract and trying to make something of it. Okay. Now here's a very nice property called the principle of independence. It says that the conditional entropy is always at most the original entropy. So if I condition on a random variable, the amount of information you're expecting to get out only goes down. Okay. And if you actually combine those previous two, you can start getting something like this. The entropy of these two random variables, x and y, as a joint distribution, okay, is at most as if they were independent. The entropy of x by itself plus the entropy of y by itself. I should note that if they were independent, then it would be equal, and also the entropy of y conditional on x would be equal to just the entropy of y, because y conditional on x has the same distribution as just y for any possible x. Okay, I know this is all a little bit fast, but maybe our goal is to first sort of take these kind of simple, at least algebraically simple rules as given, and see it in action, and then maybe come back and play with it at the end. Actually, no, I think I do have a nice identity coming up. Okay, so we're going to prove this in a really cute way using just those rules. But let's look at what the claim is. I'm looking at on the left. that looks like how many subsets of n are there of size up to Pn. Okay. And at the right, it says, oh, it's at most 2 to the n times the entropy of P. Okay, h of P is a little bit mysterious, but certainly it's quite compact on the right, so that's appealing. Now, another way to think of this lemma, what happens if I divide both sides by 2 to the n? So that's sort of like if I divide both sides at the end, then if this was like over 2 to the n, that's total number of subsets, and this was divided by 2 to the n. That would sort of be okay. That's sort of like flipping n fair coins, right? And then any outcome is possible. And then the left side is saying what are the odds of getting at most Pn heads, right? Because there's all these subsets of size at most Pn. And the right side is giving you some Chernoff-y looking bound of 2 to the h of P minus 1 times n. So I think here it's worth pointing out, maybe I should have drawn a graph. The h of P is always at most 1, okay? And in fact, it's maximized by P is equal to 1/2, which is sort of the most unpredictable coin, right? One that's completely balanced. So indeed, if I put 1/2 here, and then this becomes 2, everything is log base 2, so this becomes 1/2, and this becomes again 2. So you get 1/2 times log base 2 of 2, that's 1, plus 1/2 times log base 2 of 2 is 1. So you get 1/2 plus 1/2 is 1. And that's the maximum. If you did the derivative for P and stuff, you'll see that's the maximizing choice of P. And then as you get away, it's only going to go down. So it's some function that, uh, bends away and peaks at 1/2. It'll also be symmetric. Okay? And when you get down to 0 and you take limits appropriately, you will get 0. Okay? Because you get 0 log 1 and 1 log 0, or whatever, 0 log infinity, but it'll work out. Okay. So, okay, good. So that's another, okay, so this kind of thing is, kind of useful. It looks a lot like the Chernoff bounds we often have and things like this, right? But what I think is really cool is the proof. Okay. All right. So I want to prove this. What should I do first, or what could I do first? Sorry. Oh, like expand out all the. No, it won't expand out because I want this to be a nice proof. Yeah. Oh, that's true. That's not a bad idea, but that won't. So the suggestion was like, why don't I add the remaining sum, something like this, on both sides? That's not a bad idea, but that's not the direction we're going to go. What if I just want to like kind of get rid of this exponent? Okay, we're going to take the log. Yeah, sorry, I'm leading you a little bit because the slides are prepared. They were prepared. Oh, they were prepared. Okay. All right. I'm going to take the log of both sides. Okay. So on the right side, okay. Okay. So, okay. All right. What does this look like the entropy of? Let me do something else. So let's say that X is like a uniformly random out of K choices. Just as a different example, because I realized I didn't give this example before. Let's look at the entropy of a random variable that's just a uniformly random out of K choices. Okay. So H of P, right, is the expected value of the log of the shock, which is the probability, sorry, H of X, the probability that X is equal to whatever value it's given or something. It looks awkward because I wrote X is equal to X. But if it's uniformly at random, that's always 1 over K. Okay, so you get log K. And that's actually the maximum entropy that can be attained by something with only K choices. Okay. All right, so I say that because that's one way to try to think of the left-hand side. right? Because that's just accounting all the sums with at most Pn elements. So I can think of this as the entropy of some uniformly random set, or random set of size at most Pn, but chosen kind of uniformly at random. Because that's how many possible ones there are, and their entropy would be the log of this thing. Okay. And in the right side, well, what would 1 HP be like? The entropy of like a coin that flips heads is probability P. So this is like the entropy of n independent coins was probability P. Okay. Okay. So now I'm going to introduce two random variables. One is a random set Z, and another is indicator variables for each of those n elements. So a random set Z, this will be a uniformly random subset of size Pn, just like above. But now I'm going to make the yi's depend on Z. So yi will be 1 if I is in Z, and 0 if I is not in Z. Okay, good. Now let's look at the entropy of our random set. So just choosing out of all the sets of size at most Pn, one of them uniformly at random. Well, I can think of Z as the same thing as like the full distribution of all the individual yi's. Okay, so if I have Z, if I know what Z is, then I know the outcomes of all the yi's. If I know all the outcomes of all the yi's, then I know Z. So they're the same kind of random variable. Okay, now here's the nice part. What to do here? So to be clear, these are jointly distributed, right? Because if this one is in the set, these guys are a little bit less likely to be in the set because I'm constrained to take up most Pn elements. So they're not fully independent. Okay, so we can bound it above by using this sort of subadditive thing, right? Because it's always less than if they were independent. Okay, but now if one of these variables in isolation by itself, what is the probability of an element appearing in our set? P. So you get NHP. Okay, it's actually less than equal P, but entropy will get bigger up to P. Huh? H of yi is equal to, yeah, or it might be less than equal to H of P. Yeah, think of here. I want to think of P as less than 1/2. Yeah. Yeah. Why is it what? Well, I meant to say less than equal, but each element's going to appear as probably at most P. Yeah. Okay, good. All right, so, but it's a very slick proof, right? Okay, and we're going to use this bound in a moment. Okay. All right, so now let's prove first part of Shannon's theorem. Okay, there is a coding scheme with transmission rate approaching 1 minus h of p, this mysterious h of p quantity. Okay. All right, well, I guess here's the idea slide. Okay, so this is your chance to come up with truly optimal code. You take the other unproven half for granted, you're not going to do much better than this. So, any ideas for coming up with the world's best possible coding scheme? Yeah. Okay. So each bit will get mapped to. So this is almost at some level you're taking m equals 1 and you're going to repeat this for all the bits or something. And so Okay, help me out here. Okay, you want to take one bit and map it to a block of log of 1 over p bits. And what would those log of 1 over p bits? Would they just repeat the same bit? That mean that would kind of be an okay code because but the only thing is transmission rate wouldn't be very good. It'd be very close to 0. I mean, it'll be 1 over log 1 over p. So for every thing in the input, you want to assign something in the output. How should we assign it? Or any buzzwords or random ideas? Random in like an arbitrary sense. Miscellaneous ideas. Uh, you're gonna just add noise to your own message? Right. Mess with the bad guys. They can't mess up my message if it's already messed up. Yeah. So I'm gonna take my modest message of some size m and then somehow just try to choose random subsets to move over. Okay. And repeat some of them. Uh, okay. Now we should be a little bit careful because well, yeah, you want to recover every bit in the original message. So I feel like if you're only protecting some part of the message, you're still screwed on the emitted part. Okay, so first of all, when you say how many times we repeat that bit, there's only 1 and 0. So you could write down like there should be 10 ones and 14 zeros. You can leave some hints around, right? Maybe some kind of arithmetic facts. That actually starts getting to something called linear codes, like Hamming codes, parity codes, things like this. So you can do these kind of algebraic, oh, it solves some system of equations. There's only one solution. You can kind of map it back. Yeah. Yeah. Another idea or same idea? Okay. Oh, yeah, maybe. I mean, you said taking a random walk in a hypercube was such joy. Everyone else is like, what the okay. Well, so that's going to be Shannon's I think these were supposed to be erased. That's Shannon's great idea, which is not so obvious in 1948. There was very little randomization going on in 19 the law axioms are probably only set like 20 years before by Kolmogorov. Probably is not as old as you think. So that was his thing. Okay, I'm going to do a random code. So I'm just going to make a big list. So for every input, I'm going to assign a random n-bit string, random n-bit string, random n-bit, uniformly at random. Okay, and I'm going to look at that. Now the next question is, it's a bit chaotic, right? How are you going to decode it? Right, so you send some code here, and then it might move around a little bit and things like this, right? So, what might be an idea for a decoder to kind of random code? Yeah. Oh, uh, yeah. Could we choose a decoder first and then? Well, we're committed to this uniformly random code. How would you decode this uniformly random code? Or like what's reasonable? So if you just have some message somewhere around here, and imagine you have all the time in the world, or 2 to the m, 2 to the n isn't that big a deal. Yeah. We can look for the closest code word, right? So this is gonna map to some like scattered, subset of this space here, right? So some arbitrary point here, I can look for the closest code word and just return that. That seems the most likely. right? Okay, so that's sort of an intuitive decoding scheme. We're just going to map back to whatever, this whole region will get decoded to y because y, c of y is the closest code word to everything in this circle. So this zero norm is just some fancy way to say, number of bits that are different. Okay. All right, so that was the great idea. Let's look at a random code. Okay, actually the final answer will be slightly different. Okay, now our analysis is gonna be centered on two claims. Let's go through them slowly. All right, so fix a particular input message. They're all treated equally. With probability of error at most delta over 2. Let's say I'm going for error delta. Okay. I'm gonna flip at most 1 plus epsilon pn bits when I send it over. Okay, so that randomness is over the noise. Okay. The second claim was probability of error at most delta over 2. No other point x prime will be within 1 plus epsilon pn bits. Right? This is really saying the coded word minus the noise, the noisy encoded word. Okay. So there's a fair bit of randomness here. So I want to be a little bit clear. So in this statement, the randomness is over C, you're choosing a random code word, and the random noise for fixed x. Down here, you have fixed x and x prime, but you're still choosing random code words for both x and x prime, and you're applying noise to x. Okay? Now, okay, so good. All right, so now let's suppose both of those claims are true. Okay, so what is that saying? Okay, so with probability of error, so let's say both of those events happen. So that means that C of x flipped only 1 plus epsilon pn bits. Okay, and no other code word is within 1 plus epsilon pn bits of the noisy transmission. Okay, so the first one says that your noisy transmission flipped at most 1 plus epsilon pn bits. And your second one says no other point has a code word within 1 plus epsilon pn bits of where the noisy transmission landed. Again, a lot of randomness going on. Okay. But if both of those claims are true, then what are the odds that we don't decode our original message? That most delta, oh shit. That most delta. Okay. Uh, because, okay, so if you are within 1 plus epsilon pn bits and no one else is within 1 plus epsilon pn bits, then that closest code word will be yourself. Okay, so that just guarantees that you are the closest code word to your transmission. Okay, good. Now, so we'll prove those two. Those will take more effort and some concentration bounds and stuff. But let's just look at this. Now, our goal is to actually come up with one code that has small average error and good transmission. Okay, so good. So we want a single code. And right now, this randomness is kind of like if I chose a random input X and a random code and random noise, then the error is at most delta. The odds of not, right? But I want a fixed C. So some level, I want to pull this out. Okay, so right now, it's a little bit easier to analyze when everything is random. But at the end of the day, we wanted to show there is a code that has all these nice properties. Okay, so what can we do? Any ideas? Yeah. Okay, so the next step then, man. Okay. All right. This is the same as pulling out the expected value of C over C. of the probability of thing. And so what is this? This is saying if I choose a random code and then I condition on that code, what does this represent? Okay, what are the odds where I pick a random input, random, apply some noise? What are the odds I don't correctly transmit? Okay, so inside the condition, that's the average error of C. Okay, so what we've shown, the expectation over all random code, all codes, chosen uniformly at random. The average error of a random code is at most delta. Okay, we're getting closer. Okay, we're still looking for a code that has average error at most delta. Ah, okay. So if the average is at most delta over all codes, there must be at least one code, right? Okay. There exists some code with average error delta. Yeah. Did you want us to find this code or just prove that it exists? This is just proving that it exists. Yeah. And so this is going to launch a never-ending field of trying to find this code. Okay. And in real life, people not only want to find this code, but ideally they would also like, they don't want some like arbitrary code that's like a crazy listing of like map this to this and this to this, right? They would love it if it was it was some simple like algebraic encoding or something like this. So it becomes much more sophisticated because you also want like a compact code that's good, right? But this is still an amazing theorem. And then we'll see when we prove those claims why it's helpful to analyze a uniformly random code. Okay. So he found that analyzing a uniform random code helped him isolate the existence of some code. And if m and n is small, you can start enumerating things as well. Or you can just generate a random code, you could test it. How hard could it be to find this code? How big is m and n? Yeah. Plus, if you want something that's compact, like you just like coming from a few simple rules like linear codes and things like this, yeah, then it starts to get, you're not even promised that there is a compact code like this, right? But you can. What's the transmission rate for like RSA? Like you just give it a simple RSA. So encryption is a completely different question. Encryption is like you have a message and you don't want your grandmother to find out on the other side. So you multiply it by a big prime or something. You multiply two big primes together and say, grandma, what's the prime? And she has no idea. Okay. All right. Okay. Yeah. All right. So, but that's sort of the brilliant insight was to, because you're starting from a nothing, right? People are laying wires in the ground and they bring in this guy who had already done some nice work on Boolean circuits. Say, can you make some sense of this? And he certainly made some sense of it. But it was a really daring and bold step, especially at the time, to say, let me analyze a uniformly random code. All right. Okay, so, oh my. All right, so let's first do this direction. Yeah. Okay, so what does this say? How many bits do I expect to flip? Right? And each bit gets flipped with probability Pn. So the right-hand side is 1 plus epsilon times the expectation. Okay, so the probability that the number of flips you flip is at least 1 plus epsilon Pn is, as you all have done a gazillion times, e to negative epsilon squared Pn, over 2 or something, I forget. Yeah, I forget, I make up, I don't know, some constant. Okay, and now you just, once n becomes big enough, and also m, because m and n are kind of ratios to each other, right? To infinity, and this will go to 0 rapidly. So here you're allowed to make m and n big in this model. And that's not considered bad. Okay, so this will go down to 0 just because you don't expect that many bits to flip. Okay. Now the other one's a little bit trickier because you want to make sure that all these other code words are not too close to you. right? So now this is a different question. So this is saying, okay, so at some level you can even treat this as fixed, right? This is like a fixed point in the hypercube because conditional on that, C of x prime is still uniformly random. Say, okay, it's at some level some geometry question about this hypercube of 2 to the n and things being spread out and things like this. Okay. All right. Do I have anything to help us here? Okay, good. Save us some time. Okay. So um, let's look at a fixed x prime not equal to x. Okay. So what is the probability that this code word is in 1 plus epsilon p n bits of n of c of x, which again, you can do everything conditional on this value. You can treat that as a fixed point. Okay. All right. So what is it exactly? So if you do it exactly, you're going to get some kind of, yeah. Yeah. So this is, how many possible spots you can pick on the hypercube, right? And this is summing up. Okay, you're going to flip one of the bits, you're going to flip two of the bits, you're going to flip three of the bits, four of the bits. Okay. Remember, this one is completely uniformly at random, so it's not like they flip with probability p, right? C of x prime is chosen uniformly at random from the hypercube. Okay. Good. Now what? Sorry? Oh, the thing on the right. Okay. So you get something h of 1 plus epsilon p minus 1 to the n. Okay, so this was that cube proof that we did before. Okay, this minus 1 is coming from the 1 over 2 to the n. Okay, good. Now, if I want to say, uh, now you want to, you're worried about all x's, x primes, right? So, okay, I write for some x prime not equal to x. Okay, and what would this be? Just times 2 to the m. So if you do times 2 to the m, then it's kind of get added into the exponent. Something like this. Okay, it's like very, very hard to read. Okay. All right, so now let me just make sure I don't mess up in the limited amount of time. Yeah, limited amount of time. Okay, now I want this thing to be less than equal to delta over 2. Okay, so if I start taking like logs on both sides and rearranging, what do I get? I get m is less than equal to, okay, 1 minus h of 1 plus epsilon p. Just want to balance my parentheses correctly. Minus, I have a minus 1 here. That's from the delta over 2. Minus log of 1 over delta. Okay, looks kind of crazy. Okay, and in particular, if I now divide by n, this is the transmission rate, right? It's saying that as long as the transmission rate is less than equal to 1 minus h of 1 plus epsilon p minus some term that's going down to 0 very fast, log of 1 over delta over n, because remember, we're allowed to make m and n as big as we want. M over m and m, okay. Okay, so this is our transmission rate. Something like this. Okay. Now, I guess I didn't read this part of the theorem statement very closely. So what we're going to do is we're going to choose epsilon so small that the difference between h of 1 plus epsilon p and h of p is pretty small, at most delta over 2. Okay. And then if I do that, I'm going to get less than equal to 1. Oh, 1 sec. Okay, so as long as m over n, well, let me put it this way. So we're trying to find like, oh, if the transmission rate is small enough, then it'll be good. Okay, so at some level, if I can find a lower bound for this, that'll upper bound the transmission rate I'm going for. Does that make a little bit of a contrapositive? Okay, so 1 minus, I realize that my h's look like pluses and all this nonsense. 1 plus epsilon p minus this log 1 over whatever n term is at least 1 minus h of p minus delta over 2, because epsilon is small enough. Again, h looks like a plus, minus this something something over n term. And if n is big enough, that'll be at most delta over 2. So 1 minus h of p minus delta. Okay? So as long as the transmission rate 1 over n is less than equal to 1 minus h of p minus delta, minus maybe a little bit more, I will be able to, yeah, minus that, then this inequality, this whole thing will be okay. Okay, so all of this will come out to less than equal to delta over 2 as long as m over n is less than equal to this. Which of course you want to make n as small as possible subject to this. You want to make transmission rate as high as possible. So you're going to set m over n exactly equal to this, just to make this go through. Okay, that makes sense. Okay, so it's just kind of tight calculations. Okay, I think it's really important to point out though, this original question, what are the odds of some random point in a hypercube being in this neighborhood of a particular point, was completely handled by, that's where entropy came in, is to handle something like this. And then this epsilon wasn't very significant. We chose epsilon small. Yeah. Is that bound with the industry size? It's very tight. For small p, I think, or maybe for bigger p, I forget. Anyway, it's very good. How tight? I don't know. Plus or minus little 1, but in the exponent, but maybe that's good. Maybe it's not, I don't know. But it's well known. You can look it up online. Okay. All right. So this entropy is really coming into play in this certain kind of question about the geometry of hypercubes, which is actually the kind of dominating bit of the analysis, right? Because you're choosing random points on a hypercube and you want them to be spread out. How do you show that? You get this, and that's where this entropy is sort of characterizing. Okay. And this is somewhat tight because if you could do a much better bound, okay, here's another answer. If you could do a much better bound, then you get a much better code, but it would run into that lower bound that we haven't proven yet. Okay, so the lower bound also being roughly 1 minus HP in the transmission rate shows this inequality can't get that much better to some extent, because if it got much better, you get a bound that's so good it's going to break the bound we haven't proven. Okay, let's see if I can at least sketch. Okay, so that's the existence of a code. It was transmission rate approaching 1 minus h of p. Sort of hidden in this statement is that we're actually allowed to take m and n to be fairly big. so that concentration kick in. We use Chernoff at various points in the middle and things like that. The large M and N also drowned out that epsilon, things like that. Okay, so M and N also so can be big. And I guess ideally you'd want it to kind of be all other things being equal, you'd rather have M and N being smaller. Otherwise, if your minimum message length is kind of big, then yeah. Okay. All right. Of course, you can say, for any fixed delta, it's a constant or something. But okay, so now let's go over what time remains the lower bound. Okay, I guess we won't have time to do the entropy properties, but they're all in the notes, kind of done carefully. And probably for those properties, it's best to just repeat the calculations yourself because it's just pure math, and it works out kind of very nicely. There's like a million trick proofs based on entropy out there. They are kind of cool that I should probably put more effort into collecting and putting into exercises. But if you're interested in that kind of thing, I can help you find a survey. Okay, so we want to show that any coding scheme with transmission rate much bigger than what we just proved. Again, you should think of delta, some parameter going down to 0, has some kind of average error rate. And if I remember correctly, we'll actually be able to make the average error rate arbitrarily big. It might even be more like 1 minus delta than delta. Okay, but we'll see. Okay, no time for ideas. That was spent on Don't Open the Box. Anyone seen the movie Seven? No? You guys haven't seen Seven? Yeah, it was Brad Pitt, and he opens the box. Yeah, okay. All right. Okay, so let's say that there is such a code with such a good transmission rate. So M is very close to N is what you should be thinking about. M is at least 1 minus HP of N or something. And okay, so to set up this proof, okay, so now you want to show that the probability error must be kind of bad on an average input. And at some level, it's going to be easier if we even assume that the noise function is not that bad. Okay, so E is the event that you flip at most roughly Pn bits. You expect to flip Pn, you flip at most 1 plus epsilon Pn, at least 1 minus epsilon Pn. That's probably going to happen anyway. So you're not giving up much, but somehow like conditioning on that event is going to make that analysis a little bit easier. So when I look at kind of the average correctness rate, 1 minus the error rate of this allegedly good code, I can just say, okay, well, I'll just give you whenever that event doesn't happen, which I know is small anyway because of the Chernoff bound. And now let me figure out the odds that you get it right, assuming even your noise function isn't messing you up that much. Okay. Yeah, this C probably shouldn't be there because it's just over X, but N should be there because you're analyzing a particular C that's supposedly so good. Okay. All right. So what is the probability of not E in a word? Yeah, so this is going to be, this is just a deviation bound. What are the odds of flipping too many bits? So I'll just do both at the same time, epsilon squared Pn divided by, 1 million gazillion, whatever. That goes to 0 as, epsilon in it. Okay. All right, so that's pretty small. Now, we really want to focus on this. Okay. Now, okay, good. So let's see if this is set up. Okay. So our goal is to bound. Made that same mistake here. The probability that that this so-called code is able to decode things correctly, even assuming that the error is that not too many bits got flipped. Okay, because we've already done this term. This is just not that bad. Okay, and I'm going a little bit quick. Okay, so I'm letting y sub x be the points that decode to x that are also pretty close, I think, to cx. I think this is a mistake. That's pretty close to c of x instead of x. Okay. Well, the mistake is also in the notes, so that's great. All right. So there's typo in the notes. Okay. Yeah, I think it should be c of x. Good. Now, all right, let me just go through this. So the probability over all x and noise, let me just copy this down here. Okay, so this is equal to, I can enumerate over all x's. Okay, so I'm going to sum over all x, that are m-bit strings. And then I'm going to sum over all y. Again, we're inside this event E. The probability that x gets coded to y. Okay. And good. Okay, now what I know about y is that it differs from c of x in, I think, at most 1 minus epsilon pn bits. Okay, I wrote at least in the notes, but I think that's wrong. So this term here is less than equal to p times 1 minus epsilon. I screwed this up. Pn times 1 minus p 1 minus epsilon p n. Okay, is that obvious? I wrote it like it was very obvious. Okay, so for pn different bits, no, for this many bits, okay, so this many bit flipped. Oh, okay, so y is fixed, right? And c of x is fixed. So you need a particular set of 1 minus epsilon pn bits to flip. And this many bits to not flip. Okay. And this can be written as 2 to the negative h of p. I don't know if this is going to be a very convincing proof, given the time constraints and the fact I'm just rushing to write things down. Okay. There's no time for hows. Let me just at least go over the last parts because I'm already over time. So you're summing over all x e to the negative h pn 1 minus p, whatever this crazy probability is, epsilon pn times the size of yx, okay? Because it's the same for all the y's in yx. And you can pull this outside. And then if you sum over x, all the sizes of yx, what do you get? 2 to the n, right? Because all the y space is going to fit in the y space. And so you end up with, at most, 2 times 1 minus h of p n minus m 1 minus p over p epsilon pn. Okay? So the real problem is if this thing is much less than 1. Okay, so it's a transmission rate. If n is much smaller than 1 minus hp times m, then this is going to be start going down 2 to the negative some constant times m. So you need this thing to be positive, or else you're going to start going down and you're going to get screwed. So in that case, we said, oh, if the transmission rate was smaller by an additive delta, then this will become 2 to the negative delta n times whatever this junk term. Okay. And so this is kind of a big part of the correctness rate, right? But here's where you're getting killed. So this part's going to go down to 0 and dominate this term. And you go all the way back up, and I know my handwriting doesn't bestow a lot of confidence, but this was just a Chernoff bound showing it's small. And if we showed that if the transmission rate is too good to be true, we're able to show that this thing plummets to 0 fast as well, right? This thing going to 0 is really coming from this term going to 0. Okay? All right. So all that's really proving is that this thing is tight. I ran out of time to do the calculations well. Plus, I need to double check my notes. But what's really amazing is that even in a lower bound, he's able to pull this 1 minus h of p. It came up naturally, right? So what he was really able to show is, kind of focusing on the transmission rate, which shows up awkwardly in exponents of our calculations, right? This stuff is not obvious when you look back, like how did he kind of pull out? He gave names to this, right? People weren't talking about. He gave names and showed this is the right thing to look at, and it's clean and well behaved. And then he showed that this optimal transmission rate of 1 minus h of p. Okay. All right, so I'll stop there. Thank you. Yeah.